amplitude of the pressure was really limited. We can barely hear what he's saying. So the objective of my study is to design an artificial vocal folds that can restore the normal phonation attributes mentioned earlier, intelligibility and naturality, and etc. So the question to be answered in my research is what parameters of the vocal fold that can affect the quality of the voice produced. Those parameters include geometrical parameters like thickness, length, etc., or material parameters like stiffness or elasticity. So the methodology followed to answer this question is as follows. First, we implement the model of the vocal fold. It is made out of silicon. We choose the study parameter like stiffness and thickness, and we change it with multiple models. And this model of the vocal fold is then tested under an experimental setup to record the the flow rate, the pressure, the sound parameters like frequency and amplitude. And those parameters, recorded values are then post-processed. And then, as a fourth step, the numerical setup is used to mimic the environmental test and then to validate the experimental results. Then a statistical evaluation is carried out, like using a correlation test or significance test in order to compare between the numerical and experimental setup and to validate the result, validate the effect of each parameter study with the result of the sound. This is the experimental setup I used, consists of air source, 2 pumps that resemble the lungs, and sensors like a flow rate sensor and a pressure sensor, and of course the model holder, the holder for the vocal fold. This is the vocal folds during vibration inside of the model holder, and this is the result in a spectrogram, which is the frequency shape of a real time for the sound. You can see in the left side is the spectrogram of our model, and on the right side is the spectrogram of a synthesized voice at the same frequency. As you can see, the results showed a very similar spectrogram regarding the signal-to-noise ratio and regarding the consistency of the frequencies in the spectrogram. Then, to validate the experimental result, a simulation, numerical simulation is carried out in COMSOL multiphysics software, which is very popular in research. Firstly, a 2D coupled FSI simulation, fluid structure interaction simulation, is carried out to study the effect of fluid on the structure and the deflection carried out and the effect on the structure back on the fluid. That's why it's called coupled. A 2D study is carried out, then a 3D study is carried to more specifically see the deflection patterns, as you can see in this result, and also to see the velocity distribution profile over it. Then the results of the frequency are recorded with each parameter. As you can see, this is the graph of the result of experimental and numerical setup that demonstrates the change of the frequency, of the deflection frequency and the sound frequency, along with changing the diameter. We can see as we increase the diameter of the vocal folds, the fundamental frequency decreases. Those are both plots of numerical and experimental results of the frequency, and they showed a good correlation of 0.5 at significant p-value below 0.05. This demonstrates that the finite element numerical model can be used further to study the vocal folds. So as a future research, we hope that the data obtained from this research can be used to design a new prosthesis that incorporate vocal fold that can restore the sound for those who have lost it during laryngectomy. Thank you.
Thank you very much, Dr. for the nice presentation and for the great work as well. So now the floor is open for the Q&A. Please. So it seems everyone is satisfied from the work you have done, in fact. So I would like to congratulate you and your supervisor as well. Thank you very much. We may proceed for the following paper.